big C for capacitance. And we did a lab earlier, the Wheatstone Bridge lab, where we put in resistors in singly, in series, in parallel, in various combinations. So this is a repeat, basically, in terms of procedure of that lab, but with capacitors. The big difference with capacitors, between capacitors and resistors, is resistors simply resist. They're called a passive circuit element, and capacitors are hooked up in this circuit, which is going to charge them and discharge them. So there's a time factor here which doesn't appear in the Wheatstone Bridge experiment. So you may remember this was Ohm's law. That's the law we used in the Wheatstone Bridge lab to figure out resistance values given our setup. And we have the capacitance lab is basically, the capacitance formula is defined this way. That is, capacitance is a measure of how much charge you can put on each plate, the magnitude of the charge of a capacitor divided by the voltage. So if you can put on 1 coulomb of charge by applying 1 volt potential difference between the plates, you have a capacitor that's 1 farad. That would be a huge capacitance. Most of our capacitors are in the microfarad or picofarad or nanofarad range. We do have a capacitor in the department that's 1 farad, but we're going to be dealing with microfarads in this lab. So, and we're going to be dealing with voltages from our 6-volt battery pack, so that voltage is going to be 6 volts. We can rearrange this. First of all, you'll notice that in this expression, the voltage is upstairs, and in this expression, the voltage is downstairs. What that means is, when we calculated the resistance values, they were V over I, right? When we calculate the capacitance values, they're Q over V. So that little mathematical difference, that inversion here, is going to show up in our formulas. And you'll have hopefully driven those formulas in class, but we know that resistors in series just added, and resistors in parallel added reciprocally. So resistors in series, resistance is resistance to the flow of current through a wire, and if you add more resistance, of course, the resistance increases. So if you add one after the other in series, then the resistance goes up. In terms of this expression here, resistors in parallel, if you put 2 resistors in parallel, you provide 2 different paths for current to flow, which means there's more current. If there's more current for a certain voltage, then there's less resistance. And so this reciprocal relationship says that the parallel resistance for any combination of 2 or more resistors is going to be lower than the lowest resistance in that parallel combination. So that's what we learned in the Wheatstone Bridge lab. But as I say, mathematically we have a little bit different situation here. And so we find out the capacitors in parallel add differently. That is, capacitors in parallel add directly. Because what's the definition of capacitor? Capacitance, how much charge can you put on with a certain voltage? If you have a junction where you have a couple capacitors, then there's more charge. This is charge Q1, this is charge Q2. The charges increase because at the same voltage because you have more places, more plates for the charges to pile up on. So capacitors in parallel add directly. There's more places for charges to go, so the capacitance goes up the more capacitances you put in parallel. And in series, it's the reciprocals addition. Okay, so if you put the capacitors in series and you put a voltage across these, what happens is this voltage here is the voltage you put across them. We'll call it A, there's B, there's a voltage down here. So this, let's say these capacitors have the same size capacitance, which basically means if you use these equations to figure out, you get 1/2 VAB here and 1/2 VAB there. So they're only charged up halfway, each of them, which basically when you apply a voltage VAB and they only charge up each one by half that much, that means they look like they're smaller. You have a smaller overall capacitance. So when you add capacitors, when you put capacitors in series, the total capacitance is smaller than the capacitance of the smallest capacitor in series. So the formulas are flipped around. And you could just memorize that, but it's better to know what's going on here in terms of why is the formula for capacitors exactly the flip, the opposite of the formulas for series and parallel resistors. Okay, so again, this, hopefully you talked about this in class already, but not, that's the formula. If not, that's the formula for capacitors. Our capacitors are a little bit different. They're electrolytic capacitors. They have an electrolyte in them, and that electrolyte can be destroyed by hooking them up backwards, so please don't do that. So the capacitors are little cylindrical capacitors like this with legs coming out, leads coming out, and you'll see on this cylindrical surface, you'll see a bright band here, which is just above this lead, which is the negative lead, and this therefore is the positive lead. So be sure when you hook them up that this band is pointing towards the ground direction of the black wires on your apparatus. If you hook them in series, make sure each one of their negative terminals is pointing towards the black lead. Okay, so that's our setup. Again, there's a time factor involved. So here's what our circuit looks like. This is our 6-volt battery pack, and yes, it's a little more than 6 volts. We don't really care about the voltage. We care about how they discharge, how they will discharge with time. So we're going to put in a resistor here. This is going to be 100 kiloohms. You're going to need to measure that carefully because, as I'll point out in the demonstration of the apparatus, that is your only error source. This is the most wonderful error analysis you can have because there's only one error source. The other error source is the computer, which is far more accurate than the error in this resistor. So measure the error, measure that meter with the meter, the resistance value very carefully, and figure out the percent error there, and that is the error in your experiment. So your values for the capacitance are going to be the correct values to within that small percent, probably one or a little over 1% error, depending on the resistor value. So, and here's the capacitor. Its plus terminals here and its minus terminals here because this is the ground, and then we have a switch, what's called a single pole double throw switch. You can throw it this way or you can throw it this way. Okay. One way it connects to your power supply. The other way it basically connects this wire to this wire. You can look at the setup when you see, if you look at the schematic, you'll see how that works very clearly. So we have our Pro graphical analysis plot, and it's going to look something like this, an exponential plot versus time. You can change this time scale conveniently to make your overall graph on the screen look like that. I would do that. This is going to be around 6 volts, and depending on how far you charge it up. And this is going to be, I want you to go to, say, 1 or 2 volts. Get a nice discharge curve down here to about 1/5 or so of what it was to start with. If you start at 5 volts, make sure it goes to 1 volt or so. Then you're going to do the analysis on the curve here. This is an exponential curve, so it's like e to the minus ax, or at, I should say, because the graph here is time. So v equals v0, that would be 6 volts or so, times e to the minus at. Now, unfortunately, and we might as well go ahead and use it, the correct formula in the curve fit on this program is e to the minus ct. This is a source of confusion. This c is not capacitance. This c is, in theory, v equals v0 e to the minus t over rc. This is the formula for this curve. So I will say this distinctly: our c is not that c. Our c is downstairs here. This is not our c, if you get what I mean. So I'm going to put this c in quotes, because that's not capacitance. That's the exponent multiplying. Here it's shown a, but again, the choice you have, unfortunately, all the letters in the alphabet, they pick c. And so this c here is actually 1 over r times c. That is our c. That's not our c. Okay. Now that I've thoroughly confused you, sorry about that. So we want to graph this to get the c values, and just like the Wheatstone bridge experiment, you want to compare your the values you get experimentally to the values that you measure individually for each capacitor. So we're going to measure the value for C1 and C2 and C3 individually. Then we're going to put them in series and in parallel and in different combinations. And you can calculate using the formulas, these formulas here, the overall capacitance, the total capacitance of capacitors in parallel or series or parallel series combinations, just like you did in the Wheatstone bridge, but for capacitance. So this is what you got to watch out for. We have two c's here. One is the c from the exponent, and the other one is the c, which is really our capacitance values, times r. So very simple, straightforward experiment. Shouldn't take you too long. Again, all we want to see in the write-up, in the report, is one typical graph and an explanation of how you got the numbers from that graph to give you the value of the capacitor. That's it.